This video is going to be about quotients and remainders when we do division of integers. But before we go on, I think it's a really good idea for you to look at the in-class activities for the division algorithm and congruence problems. Just go ahead and take a look at those to familiarize yourself with quotients and remainders, and then come on back here and we'll finish the video. Okay, so as I mentioned, we're going to be talking about dividing integers. In particular, we're going to be looking at the division algorithm and its connection with congruence. So first, we're going to review how division and remainders works when we're dividing integers. We're going to make a connection between dividing and the remainders we get from dividing with congruence of integers that we've been working on throughout the class. And then we're going to state the division algorithm as a theorem. Alright, so let's look at what happens when we divide the number 6 into the number 53 and try to figure out the remainder. So our general process is we figure out how many times 6 can go into 53 without going over. So we can almost get in there 9 times. So 8 is the only number of times that can go without going over. So we look at 6 times 8, that gives us 48. And then we subtract 48 from 53 to get 5. Now the 8 that we use, that is going to be the quotient. And then the 5, from when we subtract off that 48, that is going to be our remainder. So our general process is going to look like this. We're going to divide some natural number n into some integer b. And I should note the b that does not itself have to be a natural number. Could be 0, could be a negative number as well. We're going to find the biggest multiple of n that we can get that itself is not bigger than b, right? So just like we did, the 48 was the biggest multiple of 6 that we can have, not bigger than 53. We're going to do the same thing here. Find the biggest multiple of n, but not bigger than b. And whatever that multiple it is, it's going to be n times some integer. And we're going to call that integer q. And eventually, q is an integer, and we're eventually going to call that the quotient of our division problem. Then if we want to find the remainder, we're just going to take that n times q, subtract it from b, and then so b minus nq gives us our remainder, r. So r is the remainder, q is the quotient in that equation. And one way we can look at that equation, if we want to, and it turns out to be convenient for a certain point of view, we can actually solve for b in that one by adding nq to both sides, so we get b equals r plus nq. And if you look closely at that equation, it looks very familiar to another equation that we've seen in the past. Does it? Well, it's our congruence equation, right? If we're looking at finding the relationship mod n, that tells us that b is congruent to r mod n. Alright, so let's let n be a natural number, let a be an integer. Another way of thinking about the remainder, rather than how we were thinking about it previously, we can think of it as the smallest non-negative integer r, such that a is congruent to r mod n. Remember that a is congruent to r mod n for all the remainders. We want to find the smallest non-negative one because we like non-negative numbers, right? We don't like negative remainders. And we also like our remainder to be as small as possible. So, a question we might ask is, what are the possible values of r? Alright, so let's see what happens when we take 50 divided by 7. And you could probably figure out the quotient and remainder for this one pretty quickly, but let me go through a slightly longer process so we can find some patterns of what's happening in trying to find the right quotient and the right remainder. So, we want 50 to be 7 times q plus r, where r is non-negative and small as possible. So it's non-negative, so automatically we know that r is greater than or equal to 0. That's just imposed by the rules that we have that we made for ourselves for remainders. Those are self-imposed rules. So let's go ahead and try some values of q and see why they are or are not good quotients that give us good remainders. So let's say I just randomly pick q equals 5. Well, let's see. So I get 50 equals 7 times 5 plus, let's see, 7 times 5 is 35, so I need to add 15 to get 50. And so 15 is a perfectly good remainder in terms of satisfying the relationship 50 equals 7q plus r. However, is it the best that we can do? Well, the answer, of course, is no. This remainder is too big. But the question is, why is this remainder incorrect? Well, what we can do is, to see if it's incorrect or not, is we can try a bigger quotient. Because if we get a bigger quotient, then we have to balance out with a smaller remainder to make that equation true. So let's see how this works. So let's try q equals 6. So 50 equals 7 times 6 plus, well, let's see, 7 times 6 is 42, and so we have to add 8 to get that done. So 8 gives us a smaller remainder. And notice that that 8 is 7 smaller than 15, right? When we had a quotient of 5, we had a remainder of 15. When we had a quotient of 1 more to go to 6, then our remainder reduced from 15 to 8, which is a reduction of 7. Well, can we get any smaller remainders? Well, let's try a bigger q. If we tried q equals 6, that gave us a smaller one than 15. What happens when we use q equals 7? Well, we get 50 equals 7 times 7 plus, well, let's see, 7 times 7 is 49, so it's plus 1. So again, that gives us a smaller remainder, and again, it got reduced by 7. So it went from 15 to 8, 8 to 1. Question you might ask is can we get a bigger q and a better, smaller remainder? Well, we already know the answer is no, but let's try it anyway. If we try q equals 8, which is a slightly bigger q, we get 50 equals 7 times 8 plus, 7 times 8 is 56, which means we have to add a negative 6 to get back down to 50. That's a negative remainder. We don't allow those, so that one was too big. But again, look at what happened. We went from 1 to negative 6. That's reducing it by 7. So let's see what kind of patterns that we have. We have 50 equals 7q plus r, right? And the question is, what happens when we increase our q by 1? So if we find one quotient, what happens to the remainder? Well, what happens is our r gets decreased by 7, which means that if our r right now is 7 or above, then it's perfectly safe to increase q by 1. Because if we increase q by 1, we reduce the remainder by 7. It's smaller and still non-negative. However, if r is less than or equal to 6, then we can't increase q because that's going to make our remainder negative. Anything smaller than 6 or smaller, we decrease it by 7, we get a negative number. In general, if we have a equals nq plus r, increasing q by 1 means we're going to have to decrease our remainder by n, right? When we were dividing by 7, we were decreasing by 7. When we divide by n, we decrease by n. Which means that if r is n or bigger, then it is safe to increase q, because if we increase q by 1, it will decrease our remainder by n, which makes it smaller, and since it's already greater than or equal to n, it'll still be non-negative when we decrease it by n. But if r is less than n, it's not going to be safe to increase q, because when we do, we decrease the remainder by n, making r negative. So here's what our division algorithm says. It more or less summarizes the analysis that we were doing in the previous slide. Let a and n be integers where n is a positive integer. Then there exist unique integers q and r, such that a is equal to nq plus r, and r is at least 0, because it's non-negative, but less than or equal to n minus 1, which is the same as saying less than n. Since a is congruent to r mod n, I mean, you just look at the equation. The equation is the very definition of what it means for a and r to be congruent mod n. We get the following consequence of our theorem, called a corollary. So let a and n be integers, with n being positive. Then a is going to be congruent to r mod n for some integer r, where r is between 0 and n minus 1. And just in case you're wondering, yeah, that r is going to be the remainder we get when we use the division algorithm. So this corollary is going to be a nice way of setting up some proofs by cases. If we look at our integers mod n, then we can get one case for each value of remainder that we get, r between 0 and n minus 1. That will give us n cases. Maybe you have a lot of cases, but you can still do it in cases. All right, so now that you have an idea of how a division algorithm works and how it's connected to congruence, now you can go ahead and finish up those problems on division algorithm and congruence, and that's in the PDF file included with this video.